Well, here we go with lesson 2, section 6.1 angles. This will be the one and only recording for lesson number 2. Well, let's start by converting some angles from radians over to degrees. So this is the angle theta. Remember, theta is just a placeholder. It's no big deal. Pick your favorite Greek letter, and you can use that. So theta is the angle that is 3 pi over 4, and I want to convert that into an equivalent angle in degrees. And remember that 180 degrees and pi radians are exactly the same. So 180 degrees over pi is equal to 1. When you multiply by 1, you don't change the value, you just change the look. I want the units to do the talking. So I want to get rid of radians. And so I put this as 180 degrees over pi. We cancel out the pi's. 4 goes into 180 degrees, 45 times? 3 times 45 is 135 degrees. Notice we have degrees when we're done. I wanted degrees, I wanted to get rid of radians. I let the units do the talking when I want to determine whether I want to multiply by 180 degrees over pi, or rather pi over 180 degrees. Same problem. I know it looks different because there's no pi, but that's 1.7 radians. If you don't see the degree symbol, it means radians. Well, I still need to get rid of radians, even though you can't really see the symbol. So I'm still going to multiply by 180 degrees over pi. I'll get rid of radians, cancel out radians in my mind, and I'll have degrees when I'm done. So here we go. I multiply by 180 degrees over pi. You imagine that you're going to cancel the pi out. You multiply by 180. So really you're taking 1.7 times 180 divided by pi, and that's what we end up with, 97.4028 degrees. Please don't use 3.14. Use the pi key on your calculator. It's a much better representation of pi. Moving on. Well, here theta is 2.3 radians, and now I want to convert this into degrees, minutes, and seconds. Well, we can't really do that directly. What we're going to do is take 2.3 and convert it into degrees decimal, and then from there we're going to convert it into DMS, degrees, minutes, and seconds. So we start by multiplying by 180 degrees over pi. That converts into degrees decimal, and then we use our old skills. Knock off the 131, multiply the decimal, 0.7802929 times 60. And again, that's 60 minutes per degree, which leaves you with 46.8 minutes. Knock off the 46 times the 0.8175728 minutes times 60 seconds per minute. That gets you into seconds. And then we round off. Don't round early. This is 131 degrees, 46 minutes, 49 seconds. You round off the 49, but you don't round off the minutes. We'll take care of that with that second calculation. There we go. 2.3 radians is 131 degrees, 46 minutes, 49 seconds. Well, now let's go from degrees over to radians. And remember, we're going to multiply by 1. 180 degrees is equivalent to pi radians. But now I want to get rid of degrees, so I let the units do the talking. So the degrees are on top, that 240 degrees over 1. I like putting everything in fraction. I multiply by pi over 180 degrees. I put the 180 degrees on the bottom. That cancels out the degree symbols. 60 goes into both 240 and 180, and we end up with 4 pi over 3 radians is equivalent to 240 degrees. Don't try to memorize 180 degrees over pi or pi over 180 degrees. Let the units do the talking. What are you wanting to cancel out? There you go. And here's another one. Let's convert 100 degrees over to the exact radian measurement. And again, we're going to let the units do the talking. I want to get rid of degrees, so I use pi over 180 degrees. And then you just have to reduce. The pi stays with it. I usually take the zeros out, and I've got 10 over 18. And then I realize I can end up with 5 pi over 9. I know most of you don't like fractions, but we have to deal with them. So 100 degrees is equal to 5 pi over 9 radians. Well, here's the next set of problems. If theta is in radians, then the length of the arc created by theta is found by S equals R theta. Kind of important here. So this is really from the circumference formula. We're looking for that piece on the circumference that is subtended by that central angle theta. That's why we use S. And so we use the formula R theta. Theta has to be in radians. That's really key to this. And this, again, this comes from circumference equals to 2 pi r. If I let theta be 2 pi, it would be the exact same formula, 2 pi r. So S equals r theta. The key is theta has to be in radians. All right, find the length of the arc subtended by the central angle. We're going to use S equals r theta. Theta needs to be in radians, so we're going to have to convert 60 degrees to radians. Once we have that, we just times it by the radius and we're done. And 60 degrees is equal to pi over 3 radians. You can times that by pi over 180 degrees if you want to, but get used to 60 degrees being pi over 3 radians. The radius is 10, so the subtended arc is of length r times theta, 10 times pi over 3. Get your calculators out. Don't use 3.14. Use the pi key, and you multiply, and you get your answer. I want you to check this out yourself. Don't trust me. Let's do another one. The arc is 240 degrees, so this is really wrapping around there, and our radius is 11 centimeters, so we're going to have to convert 240 degrees over to radians, times it by 11, and we'll be done. So again, 240 degrees multiplied by pi over 180 degrees gives us 4 pi over 3 radians. That's equivalent to 240 degrees. S equals r theta, so 11 times 4 pi over 3. Get out your calculators. 11 times 4 times pi divided by 3, and you get your answer. It's in centimeters. And again, do this on your calculator. Don't trust me. Well, something else we do with this is try to find the area of the sector, that piece of the pie. How much pi are you going to have here? So that's the formula. Area is 1/2 r squared theta, and that comes directly from the area of a circle, which is pi r squared. And again, if you let theta be 2 pi and you put 2 pi in there, you get pi r squared. And again, just as before, theta has to be in radians. Let's do some examples. And this comes from the first example we did in the last set. We're going to find the area of the sector created by the central angle 60 degrees with a radius of 10 centimeters. Area is 1/2 r squared theta. Theta has to be in radians. And so theta is still pi over 3 radians. Again, I multiplied that by pi over 180 degrees. The radius is still 10. 1/2 r squared theta, so it's 1/2 10 squared times pi over 3 radians. You can put that 100, that 10 squared over 1 if you want to. So it's really 100 pi divided by 6, and there's your answer. Again, do this yourself. Make sure, stop this lesson, get your calculator out, make sure you can do these calculations for yourself. And no surprise here, we'll take that second example and then let's find the area of the sector. And again, this is over half the circle because theta is over 180 degrees. So theta is still 4 pi over 3. And again, I multiplied that 240 degrees times pi over 180 degrees and reduced it to 4 pi over 3. So 1/2 r squared theta. Again, put that 11 squared over 1, and you end up taking 121 times 4 pi divided by 6, and there's your answer. And it's area, so it's centimeters squared. Whereas when we were doing arc length, it was a length and it was just plain old centimeters. The units don't have any bearing on this. You don't have to be in centimeters. You can be in inches or feet or yards. No big deal there. Let's move on. All right, let's do two things here. Find the radian and degree measures of the central angle theta subtended by the arc, and then let's find the area of the sector determined by theta. So this time we're giving you the arc length and the radius, and we want to work backwards for theta, both in radians and in degrees. Then we will use the radian angle and the radius in order to find the area of the sector. So S equals R theta, and S here is 8, the radius is 3, so we divide, and theta is 8/3. That is our first answer. That's the radian angle for theta. Then we convert that to degrees by multiplying by 180 degrees over pi. So there's our two answers. We get the 8/3 radians, and we get the 152.8 degrees. Now, if you want to, you can go ahead and convert that over to degrees, minutes, and seconds. And what I did there was take the 0.7887 times it by 60. That got me 47. And then I subtracted the 47 times that by 60. And that got me the 19. This didn't ask for degrees, minutes, and seconds. I tossed that in. I'm not going to charge you any more for that. So part B says find the area of the sector. Area is 1/2 r squared theta. Now use 8/3 because that's the angle. Theta is in radians, and we need theta to be in radians. So it's 1/2 times 9 times 8/3, and we get 12.5 centimeters squared. But don't take the 152.7887 and then work to convert that back to radians. Just use the 8/3. It was handed to you. Don't do more work than you have to. Let's do some more of this. So basically the same problem. This time S is 6 feet and the radius is 18 inches. Oh, that should send some warning signs up. The arc length is in feet and the radius is in inches. So you probably want to get those either both in feet or both in inches. And remember, there are 12 inches in a foot. So I went ahead and converted this all into inches. So 6 times 12 is 72 inches. So S is 72. The radius is 18. So theta comes out to be 72 divided by 18, which is 4. That's 4 radians. Then I convert the 4 radians over to degrees by multiplying by 180 degrees divided by pi. I get 229.2 degrees. And again, if you want to, you knock off the 229, times it by 60. There's your 10 minutes. Knock off the 10, times it by 60, and there's your 59 seconds. And it didn't ask for theta to be in degrees, minutes, and seconds, so I tossed that in. Now part B says find the area of the sector. And I will go back to using theta as 4 radians. So 1/2 r squared theta, 1/2 times 18 squared times 4. And we end up with 4.5. Well, I'm sorry, we end up with 648 inches squared, which would be a fine answer. And then there's 144 square inches in a square foot. So if you divide that by 144, you get 4.5 square feet. You should be able to make that conversion. Moving on. All right, find the length of the arc again, and also find the area of the sector. We're giving you theta, although it's in degrees, which means it needs to be converted to radians. And we're giving you the diameter is 16 meters. We don't need diameter, we need radius. So we'll need to cut that in half and get radius out of it, but I think we can do this. So the diameter is 16, that means the radius would therefore be 8. Theta, I have to multiply that by pi over 180 degrees. I get 5 pi over 18. S is r theta, so 8 times 5 pi over 18. Just use your calculator. 8 times 5 times pi divided by 18. Pretty much get 7 centimeters for our answer. Let's get the area knocked out. And 1/2 r squared theta. We determine the radius to be 8. We have theta to be 5 pi over 18. And again, just do the math. 64 divided by 2 is 32. Times it by 5, times it by pi, divided by 18. And we pretty much get 28 square centimeters. Moving on. Well, here's the same setup as the last problem. The theta is 3.1 and the diameter is 44 centimeters. Two things here. Theta is 3.1 radians. That's really cool because we want it in radians. And again, we'll have to deal with the fact that diameter needs to be cut in half. Diameter is 44 centimeters, so the radius will be 22, and theta is 3.1 radians. Don't do more work than you have to. S is r theta. Theta has to be in radians. It's already there. 22 times 3.1, and we get 68.2 centimeters for the subtended arc length. Area of the sector, 1/2 r squared theta. It's 1/2 22 squared times 3.1 comes out to be 750.2 centimeters squared. So there's a couple formulas here. S equals r theta, and area is 1/2 r squared theta that you're gonna have just to know. Life will be easier if you get to know those. All right, let's wrap up with one more set of problems here. The minute hand on a clock is 6 inches long. How far does the tip of the minute hand move in 15 minutes? And then how far does it move in 25 minutes? And this will be an S equals R theta type problem. Let's do the first one. So what do we need here? This is S equals R theta. You're going to need to know the radius, which in this case is 6 inches. And you're going to need to know the angle in radians. Probably easier thing to do would be determine the angle that it moves in degrees and then convert that over to radians. So 15 minutes is equal to 15/60th of an hour, which is 1/4 of the circle. So 360 degrees divided by 4 is 90 degrees, and that's equal to pi over 2 radians. So we've got our angle, we've got our radius, there you go. So 6 times pi over 2 is 3 pi, and the tip of the hand moves about 9.4 inches. Now this wasn't bad because 15 went into 60 really nice. But it could be 17 minutes. You don't care. You do 17 over 60, and then you can determine the angle from that. Let's do the 25-minute one. That one's a little tougher. So how far does the tip of the hand move in 25 minutes? Well, 25 minutes is, well, 25/60 of an hour, which is 5/12 of the circle. So we multiply 5/12 times 360, we get 150 degrees, and that is 5 pi over 6 radians. Again, I multiplied by pi over 180 degrees there. So our angle is 5 pi over 6. Our radius is 6. So our theta is going to end up being 5 pi, which is 15.7 inches. And that wraps it up. That wraps up lesson 2. Please get to work on the homework.